So in this video, we look at how we solve a linear system by the Cramer's rule, and it is once again another method to look at the linear system. And now, please look at the linear system from the point of view of a matrix equation. In case you forget about that, I am putting a simple example here for you to understand it. Whenever you have a linear system, and this case is simple, but it applies to a more general and bigger system also. Anyway, the fact is that if you look at the only the coefficients, you see 1, 2, 3, 4 like this, and you single them out as the coefficient matrix of A. If you do a matrix multiplication with the column vector that actually contains the unknowns, like this case, the unknowns are x and y, right? You can write it as a column vector, and that's our column vector x. This matrix multiplication is actually equal to what you have in the first row and the second row. You can do it yourself. And the right hand side is actually clear. We just have to repeat what we have on the right hand side here as the column vector B. And anyway, any linear system can be viewed in this form. And the Cramer's rule means that first of all, you look at the matrix A, which is the coefficient matrix, in terms of the columns. Let's say now, generally, let's say it is n by n. In that case, there should be n columns, right? And you are required to find the determinant of A first. This is important. And then the second step is you have to look at a couple of matrices also of the same size, but you need to change certain columns of the current matrix A. For example, I use the A subscript 1 to represent the next matrix we look at. This matrix actually has all the columns the same as the original matrix A. They are almost the same, except the first column. I would like to replace the first column actually by the column vector we have on the right hand side. You have to replace it yourself. So this matrix is not the same as A, right? They are not the same thing. They're not the same. So anyway, after doing this part, you actually need to find the determinant of A1 also. And similarly, you can define all the other matrices A subscript 2 up to AN. And the definition is quite clear. For example, for A2, you can keep all the columns unchanged, except the column 2. And the column 2 you need to replace by the column vector on the right hand side. So as you can see what's happening, for example, the last matrix is gonna be having the same columns all the way, just like what you see in the coefficient matrix A, but you need to replace just the last column by the column B, you see? So in that case, there are quite many matrices you have to look at, and for each matrix, you need to compute the corresponding determinant. And now the Gramos rule means that we can actually get the solution to each variable based on all these determinants. So let me put it here. So because we are looking at a system that actually has the coefficient matrix of size n by n, let's assume that now you actually have n unknowns and they are written as x1 up to xn. And the solution to each variable is gonna be, for example, like the first one, is the determinant of A1 matrix divided by the determinant of A. And similarly, for the remaining variables, you can easily find the solution of it based on a similar formula. And that's the way to find all the solution to such a system. And let's do a problem here. So please look at the current system. It is a 3 by 3 case for the coefficient matrix. And I can write down the coefficient matrix first, like this. And now you have to find the determinant of A, and I trust that you're able to do it. Let me write it down here. So the determinant is actually -7. And let's write down the matrix we would like to look at, the next part, and we need 3 matrices, remember. And for each matrix, you have to replace the corresponding column by the column vector we have here. So for example, for the first matrix, we have to use the column vector we have here for the column 1. And the remaining entries are the same as what you have in original A. So it's like this for the A1. And let me write down the remaining 2 matrices also. So you see, these are the 3 matrices you have to look at, and you have to find the determinants of them one by one. So the determinants should be found in this way. So these are the determinants of the three matrices correspondingly, and from there you can actually arrive at the answer of the three variables. So you see basically means is 1, y is 2, and z is 3. And that's the answer to the system here. And let me write a final note here. And the note is that the current method, which is called the Cramer's rule, is only applicable to systems that have exactly one solution. And it just doesn't help us at all if the system actually has infinitely many solutions or no solution at all. And the other note is that that's the reason why almost all people still prefer to use the Gaussian elimination in many cases, because it is actually more useful. It applies to all kind of linear systems also. And that's the end of this video.